Good evening, everyone. I hope you're all doing well tonight. I'm presenting on behalf of my team, Team 3. Our presentation is on prediction of house prices, so let's get started. So today we will be discussing the project overview, the problem statement, the data understanding portion, the data processing portions, the models and the validations, results and discussions, and our conclusion. This is a flowchart for the problem overview for this project. This concept is based on cross-industry standard process for data mining methodology with sequence of 6 steps. The first step is to identify and understand the problem statement. This is followed by data understanding and data processing. In these steps, raw data is obtained and the problem is understood. The next step is data processing. Data processing we will get into more details later into the presentation. The pre-processed data is then used for model building. After selecting a suitable model, the models were tested, results and processes are reviewed and evaluated, and finally the project results are summarized and reviewed in the conclusion and future steps section. So let's officially dive into the project. Problem statement. It's important to understand the problem and the objectives. Thus, a problem statement is developed. In this project, properties prices is one of the most important criteria when buying a property. Home buyers, home sellers, real estate agents, economists, and bankers are all interested in house prices. There are many attributes that affect house prices, such as overall quality of the home, the year it was built, the number of bedrooms, etc. Since these attributes are settled, it is difficult to draw a conclusion as to which one of the factors influence the house prices heavily. Hence, a predictive model is a great tool to tweak development of properties to put more emphasis on the quality that increases the value of the property. In this study, we build a machine learning predictive model to predict the prices of property. Many models were built, including linear regression, ridge, lasso, PCR, and GAM. Among each of the models, the appropriate model was chosen and compared. Through these past slides, we grasped a clear understanding of the problem statement. Now, let's shift our focus to understanding the data. In order to appropriately understand the data, we collect the data, which was provided by Kaggle. We began with data familiarization. This is where we examine the property of the data, including the quality. In this project, the house trained dataset used to build a predictive model for a response variable price, as the sale price in the test dataset was not provided by Kaggle. The classification or the taxonomy of the data type in the data acquired has to be understood and identified as well. The training dataset consisted of 1,460 rows, the total of 79 attributes, of which 43 are categorical and 36 are numeric. It is also consistent of one numerical response, which is the sales price. This slide shows us 2 histograms, an example of numerical variables. The histogram on the left shows us the frequency and the sales price, while the histogram on the right shows us the frequency and the year remodel added. Note that the data distribution for both histograms are not normally distributed. The histogram on the left is skewed to the right. On this slide, we have an example of a categorical variable. The pie chart and the histogram both show the frequency and the overall quality. The diagrams provide us with a visual representation for the categorical data. As shown, there are 10 levels for the overall quality of homes. Initially, we were hoping to use principal component regression, PCR method, to narrow down the predictors automatically. As you can see on the slide, things didn't go quite as planned. The graph blew out. This is mainly due to the large number of factorial variables with multiple levels and data collinearity. Hence, we resorted to using a different method for processing the raw data, which will be explained thoroughly in the following sections. So let's shift our attention to data processing, which is the next step after data understanding. The final dataset, which is the process data, is constructed from the initial raw data. There are 6 phases in processing the data in this project. First step is to obtain the raw data, which was provided by Kaggle, clean the data, select important predictors, remove collinearity, and remove outliers. So in the following slides, I will get into great details for each step. Now we will discuss each step in great detail. The raw data used in this project consisted of the training data set. To start off, the raw data, just to reiterate, consisted of 79 predictors, including 43 categorical, 36 numerical, and only one numeric response, which is sales price. The second step in the process is data cleaning. The raw data has noise, missing values, and inconsistencies. Hence, the quality of the data is compromised. This will consequently affect the study's results. Therefore, data is cleaned. The data consisted of predictors with missing data or NAs. There are multiple approaches to overcoming this hurdle. Some include removing predictors with more than 200 NAs. Additionally, if the NA is smaller than 200, the data is replaced with the average value of the numeric data column. Lastly, NA is replaced with none for the factorial data. Now moving on to selecting important predictors. Initially, the predictors are grouped into numerical and categorical. Then, the correlation between sales prices and predictors are calculated. The goal is to understand how the predictors contribute to the response variable, the sales price. Different thresholds were tried, and only one suitable threshold for numerical and one for categorical were chosen to keep the number of predictors at a reasonable level. The next step is to remove collinearity. Collinearity refers to a situation where two or more predictor variables are closely related to each other. The next step is to remove predictors that are highly correlated. We used core to check for correlation for numeric predictors and Hector to check for factorial ones. The plot represents attributes with correlation to each other for categorical and numericals. Predictors that are highly correlated are identified and removed. After selecting important predictors and removing predictors that are highly correlated, the dataset was narrowed down from 79 predictors to 17 predictors. These predictors include the overall quality, the year built, the basement size, etc. During data understanding, we understand that the data distribution for sales price is right skew. As sale price is the output, which is the response, therefore the data for the sales price had to be converted to a log term before it could be used in modeling. The final step in data processing is removing outliers. In this step, outliers in numerical attributes are identified. If the data is more than 4 sigmas or less than -4 sigma, the data is removed. The example is shown in plot 1, shown as an outlier data point. Note, the outlier is removed as shown in plot 2. This is a great depiction of our project. So in this project, we used 10-fold cross-validation on all models. The cleanest of data set were divided into 10 sets. The sizes were almost equal. Every time one set of data were set aside for testing, others were used in model training. Models were built by our best subset with different predictors, ridge, lasso, PCR, generalized additive model. The average of the test errors were calculated. The appreciated models were selected per one standard error rule and minimum test error rule. The whole set of clean data was used again to select the model for testing. The result of linear regression using the best subset algorithm shows us that as the number of variables increase, the mean test error decreases. Per one standard error rule, the model with minimal predictor is the one with 6 variables. The first 6 variables are overall quality, year built, the total basement square feet, the living area above ground, garage for cars, and air conditioning. All this have a positive effect to the sales price. Then we find that the predicted results for the 6 variable model and the sale price on the right. The second model that we used in this project is the ridge model. We also used the 10-fold cross-validation on the ridge model. To determine the best lambda in the ridge model, one needs to look at the lambda that generates the minimum mean squared error for the validation data. The best lambda is 0.034. The graph on the right shows us the prediction result. The prediction RMSE for the ridge model is 23,852. Lasso is the third model. It is similar to the ridge model except for the difference in the value of alpha. The best lambda is the one generated with the minimum mean CV error from the validation data, which is 0.000266. The graph on the right shows us the prediction results. The prediction RMSE for the lasso model is 23,280. This slide shows us the result for the PCR model. The figure on the left shows that more components result in a less MSEP. The figure on the right is the relationship between the estimate price with 25 components versus real price. The last model that we used is the GAM model. For this model, we used the same predictors that we selected in the best subset model. Just like other models, we used the 10-fold cross-validation. The left figure shows us the relationship of mean error and degree of freedom. Per one standard test error rule, the selected model has 5 degrees of freedom. The figure on the right is the estimate price versus the actual price. This is the table summary. The model chosen by one standard error rule is the best subset with 6 predictors. The best model is PCR with 25 components because it has the lowest testing RMSE. As the number of predictors increases, the error rate will decrease for both testing and training data. In most cases, the training error is smaller than test error. This chart shows us the test RMSE. Actually, you can find out that after predictors increases to a bigger than 6 predictors, the model performances are similar. The GAM result is better than the linear model with the same number of predictors, but not significantly. This table shows us the important variables and its effect on the predictors for different models. The plus sign indicates a positive effect and the minus sign indicates a negative effect. For example, if the year built number is bigger, which means the house is newer, the price will be higher. In another way, if the garage is not finished, the sales price will be lower than those houses with finished garages. This slide demonstrates a prediction example. Using a house built in 1988 with an overall quality level of 7, with 2 full bathrooms, 7 rooms, 2 car garages, 1 fireplace, central air, with a paved driveway, etc., etc. Using these characteristics, we use different models to predict the estimated sales price. As you can see, all these sales prices are relatively similar in all models. In conclusion, this project begins by data processing. The data is cleaned by checking correlation to sales prices and removing outliers. All the models are developed using 10-fold cross-validation method. The results show that best subset with 6 predictor is the minimal model 1 standard error rule. Best subset, ridge, lasso, and PCR has similar prediction performance in this case study, while PCR has a slightly lower RMSE. Perhaps future studies can expand on more flexible models such as SVM and ANN, and next steps should include deployment. Well, ladies and gentlemen, that is all for our presentation. Thank you so much for your time, and I hope you enjoyed our presentation.